Welcome to the Cow Corporation's series of videos about software engineering. The topic of this video is events in multi-threaded programming. Before proceeding, make sure that you have already watched these other videos first. Let's consider this example program which normalizes a vector. First, it does step A, which computes the norm as the square root of the sum of the square of items. Then it does step B, which divides each item by that norm. That norm is stored as a data member named m_f norm. Next, we've decided to change this single-threaded program into a multi-threaded program, where those two steps are being done in two different threads. But now we've introduced a problem. Thread B might try to use the norm value before thread A has had a chance to fully compute it. That's no good. One solution is to use an event. An event is a kind of signal that's communicated from one thread to another thread. An event's implementation could be as simple as a Boolean flag within a critical section. In this example, what we need is an event whose Boolean flag indicates that thread A has finished computing the norm. Let's make sure to initialize that flag before either thread has had a chance to get started. When thread A is done computing the norm, it will now communicate that event to thread B by setting the flag inside a mutually exclusive critical section. Notice that we're synchronizing access to this Boolean flag. Thread A and thread B both have access to this flag, and thread A may be setting it at the same time as thread B is testing to see if it's been set. But notice that the m_f norm variable is different. Yes, thread A and thread B both also have access to that m_f norm variable, but they never try to access it at the same time. Thread A only accesses it before the event has been communicated, and thread B only accesses it after the event has been communicated. So we don't need to establish any critical section involving that m_f norm variable. Now, let's look at the other half of the critical section, where thread B is accessing that flag and not proceeding to do its work until after it detects that flag has been set by thread A. For this wait a little bit of time step, thread B isn't going to be doing anything while it's waiting, so it would be wasteful for the computer's CPU to be in this thread B. During that waiting, the CPU might as well be off doing some other work for other threads. That's what this sleep for function does. There's still one final detail to worry about. Imagine thread B is here waiting inside this sleep for step. While it's waiting, thread A finally finishes its computation. Thread A would like to set the event's flag, but it can't because thread A can't enter the critical section. We are still selfishly hanging on to the mutual exclusion while we are sleeping. To fix that, inside of this while loop, we need to let go of the lock and then relock it again after we wake up before we loop back to retesting the variable. In our video about locks, we defined this unique lock type as a wrapper around a raw lock, something like the way a smart pointer is a wrapper around a raw pointer. The fact that we're sleeping for 100 milliseconds before rechecking our event's Boolean flag is somewhat arbitrary. Maybe it's not as responsive as it could be, or maybe that's checking too often. It really depends on how fast thread A is going to be with its work. A less arbitrary approach would be to sleep forever, or at least until thread A is done. When thread A is done, in addition to setting the event's Boolean flag, thread A would need some mechanism to wake us up. That waking up mechanism is provided by an event condition variable. An event condition variable encapsulates our sleeping request along with the entire while loop. Thread A will call this notify1 function to wake up the other thread. It should do so after it's set the event's Boolean flag, but while it's still in the critical section. We've programmed thread B to sleep because of the event condition variable, and it will get woken up by thread A when thread A has finished its work. But unfortunately, thread B might also spuriously get woken up at other times too. Various things are happening in the operating system interrupts, and other causes that are beyond your control, which might cause thread B to get woken up from time to time. So you cannot assume that just because thread B woke up, that means thread A has finished its work. No, not necessarily. Consequently, C++'s implementation of this wait function call will cause you to sleep until you get woken up. Then it'll test some condition. If that condition determines that you had gotten woken up because of event communication from thread A, then the wait function is done. Otherwise, the wait function will automatically put you back to sleep and repeat its process. The condition that it tests is something that the programmer must provide, because it depends on the event's Boolean flag which the programmer has defined. Specify that condition as a predicate callable object which you pass to the wait function as a parameter. We prefer not to use unique locks and instead just use raw lock primitives. You can do that and still use an event condition variable, but then you would need to name its data type as condition underscore variable underscore any. It is slightly less efficient.